Good morning. Welcome back to Physics for the lab. Last week we were looking at electric forces, and we did some measurements of electric force and electric charge. This week we're moving on and doing some measurements of electric potential, also known as voltage, and electric fields. So we've been talking about this in class. But today's lab, electric potential and field, and our objective today is to do some measurements of electric potential, of voltage, and use those to also determine electric fields. And so that's what we have listed for the goals for the day. Now, the way we're going to do that is we've got a setup here. We'll be taking a look at here in just a minute. But what we're going to do is we're going to be looking at different geometry conductors. So this is what I'm going to call the parallel plate conductor. Now, this is just a diagram of what we're going to be using to make the measurements. We'll see what these things actually look like. These solid areas, or these darker areas, are conductive regions. We're going to be taking a battery and attaching that to these parallel plates. Now when we attach a battery to it, what will happen is we'll set up a voltage difference or an electric potential difference between the two plates. That means that we can go in and measure how much electric potential there is between the plates. We can also go in and measure electric potential at different locations between the two plates. So what that's going to look like, first of all, starting from here, here's this conductor that I've drawn in green, I guess. So here is a piece of conductor. We're going to attach a battery onto this. That's going to set up a voltage or an electric potential between the two sides. Now the batteries are at 1.5 volts, but because of some of the wiring and that, we're not sure how much of that 1.5 volts will show up between these two plates. So we'll see. We'll get a chance to go in and measure that. Now, across the region here are 7 different locations that are designated by kind of a coordinate system. So what that does is these points that we have along the way here allow us to go in and do measurements at specific locations. So that gives us a reference that we can compare with. So the plan here then would be to designate the center point as 0 volts. Now that's arbitrary. We could have designated one of the plates as being 0 and then measured everything relative to that plate. I guess I went with picking something right in the middle of 0 because I think it's useful for you guys to start thinking in terms of what does negative voltage mean compared with positive voltage, and it's really just arbitrary. So the important measurable quantities here is how much voltage difference do we have between 2 different locations in that region. And so by designating this middle one as 0, then what I can do is I can take in the voltmeter and start making measurements at these other locations and find out how different is the voltage at those locations compared with the voltage at the center. We're going to use the center as our reference. That says that one side on this is going to be positive voltage, kind of by definition, and then the other side, when we attach the voltmeters, that's going to show up as negative voltage. And you go, yeah, the positive negative stuff is in some sense kind of arbitrary here. We could have designated any location as 0. If I had picked one of the plates as being 0, let's say this negative plate, then moving towards the positive side would have been ever increasing positive numbers. Everything would have turned out to be a positive voltage. If I designated this plate as being 0 volts, everything here headed towards the negative side would have been more and more negative. So again, it's just differences in electric potential that are going to be meaningful for us, especially when we get to start looking at circuits. All right, so what we want to do then is, and here's kind of the steps outlining, first thing we want to do is use a voltmeter and just find out what the potentials are. Just read some numbers off of a voltmeter. So I'll put one end of the voltmeter here. Voltmeters have two wires. So in class, we've been talking about electric potential as the difference between two locations. And if I put one wire here and another wire here, I'll get a reading that tells me how different the two voltages are. And so that's the idea with step one. So we'll put one reading here, put something at the 0 point, and then put another contact point here, and successively come up with measurements on this side. We'll also end up, I guess I could draw these in. Didn't want the diagram to get too cluttered, but by the time we've done both sides, we're going to have these 7 values of potential mapped out, or measured. Let's not say really mapped out so much. Now, the second thing we want to do is map these potential, I put V in for potential, equipotentials. Now, for this we're going to use something called the galvanometer. Our voltmeters are actually so sensitive that it's hard to get a stable reading. The galvanometers are a little less sensitive. They're not jumping all over the place. But what we want to be able to do is go in and identify all the locations that are at the same potential. That means that what we're reading are zeros. Whenever we get a 0 reading, let's say I put one end of my voltmeter here, or my galvanometer, and another reading here. If it reads 0, those two are part of the same equipotential surface. And then I just keep moving farther out. I leave one of my contacts in the middle, I take the other contact and keep moving it out, trying to find those locations that are at the same electric potential. Now, with the equipotential plates, with the parallel plates, there's a lot of symmetry going on with these parallel plates already. And what we're guessing is that if I take that central line, I'll bet the equipotential runs almost uniformly, kind of halfway between those two plates. And that turns out to be approximately true, but these sheets, let me show you, they're right here. Let me grab one. So the sheets themselves, let me grab one on this other table. The sheets themselves look like this. So that piece of paper was just a drawing. This is what they actually look like. So what we've got here is, here's the parallel plate setup. And this is conductive material, the silver area. And then I've got all of these numbers drawn here on to designate different locations. And then the darker region is kind of a carbonized material, and that's got higher resistance to it. And so when we attach a battery, let's say we take a battery and run maybe a positive contact here and a negative contact here, we're not going to have much current going through here. The current traveling through here is really small, but we will be able to set up a set of voltages that are easily measurable with our voltmeters. Okay, so that's what these things look like. So by the time we're through mapping this out, what we'll have is, well, I've shown what this looks like partially. Let me show what the whole thing might look like once we get the rest of it filled in. So this is a bit of a long process, a little tedious. So let's say we start off with some contact point in the middle, and we work our way out in both directions. So we're looking to see if there really is a symmetry. Maybe there's not. These sheets of resistive material, they're not necessarily uniform, right? There could be variations in the sheet. And if there's variations in how these were manufactured, it could easily be that we don't have a set of equal potentials that are symmetric. We'll see. Typically they come out close to being symmetric, but not exactly. Even with very careful measurements, we typically can see some variations in those sheets of material. So let's say that we do one set of measurements, and then what we do is we draw in that equal potential surface. So here's an equal potential surface. In this case, it is pretty symmetric. It's running right through the middle. Next item that we want to do then is, let's move off to a different one right here. Now once I'm off center, what typically happens is this. As long as I'm moving between the two plates, I'm still getting more or less a straight line. Those parallel plates are going to give us equal potential surfaces that run pretty much parallel to the plates as long as I stay in the region between the plates. But once I leave that region and go out farther away from between the two plates, typically what happens there is we start to see this divergence. So this is really interesting to map out over here and see how that divergence takes place. So let's say we map this out and I've got this, and I am seeing this curved effect. Well, I want to do the other side. And so I've got to map this out. And so I'll have a second line. Okay, so we're doing step 2 here. We're mapping out the equal potentials using a galvanometer. And we're going to keep doing that, just to show you guys what a completed diagram might look like. Now I'm going to have to do this for you guys, which I will be doing. Okay, there's one side completed, but I still have the other side. So, and you know, in a typical lab, this might take an hour or so to carefully map out all of these. So I will be your lab partner. I will be providing, okay, so that's what it's going to look like. I'm going to have 7 equal potential surfaces. Now they're just lines because they're on a flat sheet of paper, but in general, these are two-dimensional surfaces of equal potential. So step 1, we found these numbers, filled them in. Step 2, we mapped out the equal potentials. Now from this, what we can do is we can draw electric field lines. Now in class, in the textbook, they've been talking about if you're given a set of equal potential surfaces, the way to draw E field lines, well, in this region down the center, it's not very hard to draw the E field lines because the E field lines need to run perpendicular to the equal potential surfaces. So I'm just making sure every time I cross an equal potential, it's crossing at 90 degrees. That's kind of the idea. So this is, you know, this is kind of the artistic portion of the course. Coming up with these lines that cross perpendicularly. And then I want to label this, so I'll say, I keep changing colors, I apologize for that. So on this graph at least, the E field lines are in red, and the equal potential lines are in blue. And yeah, somehow I have managed to, oh no, they're the same here. Okay. Oh, that's pretty good. All right, good. I thought I had them backwards on the other diagrams. And so when I'm in the region in between, it's not very hard because everything's parallel and I can just make these perpendicular lines. when I get out to here, I'm going to have to be more careful. Now, the E field lines do not have to run all the way up to a plate. So the first thing to realize is I don't have to draw the E field lines so that they terminate on a plate. I do have to draw them so they're crossing perpendicularly. Now, I did okay. I guess it's kind of hard to be explaining these and draw them carefully at the same time. Yeah, it looks okay. So these are the E field lines. If I moved out here, this would be an E field line. Now, the E field lines should have arrows on them. The E fields are vectors. And the E field lines should be directed away from positive charge towards negative charge. So I'm going to need to identify which end of the plates, which plate is attached to the positive terminal of the battery and which plate is attached to the negative terminal of the battery. So that's going to be important. All right. And then I need to do that on the other side too. I will try and be, oh, I don't think I curved quite enough on that last one. Oh, that one looks pretty good. So that's what the whole finished diagram is going to look like. Now, for today's lab, that's your results table, right? There's not really a results table filled with a bunch of numbers in them. What there is there's going to be the diagrams that you've drawn following these steps. So I've got the potentials drawn in. I'm going to have these numbers labeling the equal potential surfaces. We're going to map out the potential. That means identifying where the, I'm going to make little X marks and then draw those blue lines to show where the equal potential surfaces are. And then from those, we can draw in the E field lines, making sure we're crossing equal potentials at 90 degrees each time. And then finally what we want to do at some random locations, I think maybe five or six locations. Let's pick some random locations and calculate the electric field. Now, I could calculate the electric field in this region between the two plates. That's going to be easy, relatively, because everything's easy to measure in there. But as an example, so for an example to show you guys how this works, I picked a point out here. So I'm going to call this point A. Now notice I didn't pick a point on the equal potentials. I picked a point between two different equal potentials. And that's because in order to calculate the electric field, at some location can be determined by taking a derivative of the potential with respect to distance. So, the strength of an electric field will show up as a rapidly changing equipotential pattern. So it's a derivative. It's how much does the potential change for a certain amount of distance. So for example, let me pick another point in here. We'll do a comparison. So let's say, here's a set of electric field lines out here. Let me pick point B in here somewhere. So I picked point A out here. I'm going to pick B in an easier location. Now, point A has a lower value for the electric field than point B. And the way I know that from my diagram before I ever do any numbers is that, notice that this point B right here, if I do a measurement in this region, that difference in potential is the very same as the difference in potential out here. I've got two equipotential surfaces, they're spreading out. And that means that the distance between those surfaces is increasing. So what happens then is I've got the same difference in potential, but it's between larger and larger regions. So, if I calculate the electric field at A, it's going to be lower. If I calculate the electric field at B, it's going to be a higher value. So what I can do then is, well, pretty much follow this formula. So what we're really doing is finding the magnitude of the electric field. And we can do that, we can get an estimate by taking delta V and delta X for that location. So there's going to be some data tables on the graphs. You need to identify where points A, B, C, D, E are located, and then show what the delta V's are for that region. And then we got to measure distances. Now that's a little tricky because I need to measure the distance not between these 2 points directly, but I need to follow the distance along the E field line. So I need to get a curved distance for that. And to do that, I just get a piece of string, or I can get a piece of wire. And what you can do is you can take a wire and put it right along where the E field line is drawn so that the wire curvature matches, and then straighten it out. So you can take a curved wire to line up the distances, straighten it out, and then measure it with a ruler. Okay. All right. That's the whole idea here. So I've got a setup here. Let's take a look at the setup, and we will see how this is going to work. All right, so this is what the setup looks like. What I've got is, I've got one of those sheets, and you can see that I've now attached it onto this platform, and I've connected some wires, and those wires are running to my battery. Now the battery is a 1.5 volt battery. If I take my voltmeter, which is over here, and set it and place it across the battery, it's going to read something like 1.5 volts. Let's see what it does read. It's actually reading 1.2 something. So, so that's interesting. The battery's not reading full voltage. I know the batteries are due to be replaced. In any case, that's not a concern for us right now. So for us right now, what we want to do is what we talked about on the board. What I'm going to do is place one of my references right here. So I got a voltmeter, and I've got a couple of wires attached to the voltmeter. And so what I can do is I can take these two contacts and I can place them just like I did just now on the battery, and I can find voltage differences. So I'm going to start with this point right in the middle. We said I want to use that as a reference, and so that's what we're going to do here. And then what I did was I went one row at a time and measured out different potentials. So I'm measuring right now on the negative side. Very roughly, this is going like 100, 200, 300 millivolts. And then I did the other side and saw pretty much the same pattern. Now, the voltmeter is giving me those numbers, so I'm reading the numbers off of here. And you can see they're jumping around. And so in some ways, this voltmeter is almost too sensitive for us. If I want to zero this out, I could set these in contact with each other, and yeah, it's zeroed out. Okay, so, but almost every other location, it's going to show me a couple of millivolts at least. Now what I did was I wrote all these down. So I've got the zero in the middle, and then in the positive direction, I read numbers off of 119, 217, 351 millivolts. And then in the opposite direction, 101, 190, 286 millivolts. So that was the total voltage that I saw across those plates. Now what I want to do, that was the first step. That was identifying the potentials for each of those 7 points running across the center. Now what I want to do is turn off my voltmeter. I'm going to turn this off. And I'm going to bring in, instead of my voltmeter, I'm going to bring in the galvanometer. Now, the galvanometer actually has an analog scale. that I can watch. So the galvanometer is going to measure any current that happens to be traveling through these wires. And I am setting up electric potentials on the sheet here. And that says that I'm going to be able to measure some kind of current depending on where I place this. So again, what I'm going to do is I'm going to use a reference. I'm going to put one of those contacts right in the middle. Now that doesn't do anything. But notice that if I place another contact at one of these different potentials, suddenly that just jumped off scale. So the galvanometer still is fairly sensitive. Now what I'm looking for are places that are at the very same voltage. I'm trying to map out electric or equipotential surfaces. And so notice that if I kind of go back and forth in this region, I'm going to get a 0 right there. Now that actually lines up pretty well with my original contact point. Now I'm going to come out farther, and again I'm going to go back and forth until it zeros, and then I'm going to write that down. So what's happening here is this. I've got a plate that looks something like, well, you can see the parallel plates here. And then what I have is I've got some paper that has been printed. So these paper prints look like the conductive material. It's got the same pattern on it. So what that means I'm going to need to do is, you know, maybe we have somebody in the lab group who is keeping an eye on these zeros, and then someone else who sees where that's placed and they're drawing some X's. So what's going to happen on these sheets of paper is that I'm going to get a series of X marks like we showed on the board, and those are going to keep track of the equipotentials. So once I get a full set of equipotentials, I can draw lines through those, and then I can move on to the next point. So I'm just curious here. Let me see how symmetric this really is. If I come outside of the parallel plate region, it's pretty symmetric. Okay, so that's showing up just a millimeter or two off from where that halfway point would be. Now let me come over to a different point. In fact, let me come over, I'll try this one right here. So with this one right here, what's happening is, let me see where the zeros are, right there, which actually is a little farther from the plate. And then right here, right here. And then once I get outside of the plate, this is typically where we see, well, not such a strong curve. Maybe we need to come all the way out to here. Even then. So these aren't diverging, you know, as much as I showed, I guess, on the front board. Let me try this last one to see how that compares. And now on this one, I am seeing a lot of curvature around that edge. So that's surprising, actually. Maybe I just need to come out farther. Yeah. So we are seeing that effect of where the equipotential surfaces, the lines, are running pretty parallel to each other through the region where the plates are. And then once I'm outside the plates, then they begin to spread out. Okay. So that's it. That's how this is going to work. Now, I always feel like this is the easier one to start with. And then what we want to do is move on and try the very same setup. But this time, we're going to be using what I call the dipole. So the dipole, there's a positive region here and there's a negative region here. Now it's not just these points here. This other conductive region is part of that also. But anyway, in this case, we're expecting that we'll begin to see divergence right away. Right? We're really going to have to pay closer attention on this one in order to map that out and get a reliable set of equipotentials. All right? So let me know if you've got any questions let me know and we'll get those answered. Email or better, stop by office hours and we'll take a look and see what you've got.